Thank you very much for that kind introduction, and thank you to the organisers for inviting me to come and talk to you today about some of the recent work we've been doing in Oxford, trying to understand what happens to high-temperature superconductors when we put them into the harsh environment of a nuclear fusion reactor. Is that working now? Yeah. Okay. It's going the wrong way. There we go. Okay, we're ready. So what I'm going to talk about today in 4 stages, really. I'm going to just do an introduction to fusion applications and why we need superconductors for them. In particular, why high-temperature superconductors are becoming more important in this application. Then I'll give an introduction to the radiation damage of REBCO, so rare earth barium copper oxide superconductors, like IBCO. Before talking about some of the specific experiments we've been working on in Oxford to try to understand this radiation damage. Goes the other way. There we go. So we all know about the discovery of superconductivity by Onnes in 1911, but he very quickly, after discovering superconductors, realized that one of their potential applications might be in generating high magnetic fields. But he was very disappointed a few years later when he tried this out and discovered that the kind of superconductors he was working on, the elemental superconductors, really didn't stay superconducting in very high magnetic fields at all. So here for lead, he found that about 0.1 of a Tesla was enough to stop it superconducting. So this was very disappointing for him, and it really wasn't until the 1960s when there was a breakthrough in this, and that was by Bell Labs, where they reported in niobium-3 tin, which had been discovered quite some years earlier, that they could engineer it to have critical currents of 10 to the 5 amps per centimetre squared at over 8 Tesla. So this was the first real high-field superconductor that we had. And in fact, in this very first publication, you'll see over here in the abstract, that they realised that this could be used for containing plasmas for nuclear fusion reactors, right back in the 1960s. So why do we need superconductors for fusion reactors? Well, we don't need them for all kinds of fusion reactors, but a lot of the most mature technologies in this area use magnetic fields to confine the plasma. So the plasma is just a collection of ions like hydrogen, which is what we're going to fuse together, in a sort of gaseous type phase. In order to get fusion to happen, you need a high density of the ions in the plasma, so that's the N. Oh. That's the N in this equation. You need a high temperature, and we're talking about 150 million degrees C, so very, very high, and we need to confine it for as long a time as possible. So the magnets are there to make the plasma dense enough and to confine that dense plasma for long enough for fusion to happen. We can't use real materials for this because the temperatures we're talking about is 150 million degrees C. We're never going to be able to get a material close to that kind of temperature. Now, the other point to make is that the fusion power essentially scales as the magnetic field to the power 4, which means that the higher magnetic fields we can achieve, the more fusion power we can get. So increasing magnetic fields are desirable. And for people working in superconductors, you'll immediately realise that if we need high magnetic fields, then superconductors are a good way to do that. There's 2 kinds of device, magnetic fusion confinement devices. One's a tokamak. This is the most mature technology, I think most people will agree. And the other kind is a stellarator. And both of them are being explored. And both of them are superconducting magnets are being used for. So ITER, which is being built in the south of France at the moment and has been in design since the late 1980s. This is a superconducting fusion device. It has 18 toroidal field coils. These are the D-shaped coils here, which essentially do the main bit of the confinement of the plasma. They need to work at about 12 Tesla, so niobium titanium wouldn't work, so niobium-3 tin has been used instead. We have other important components like the central solenoid, which is also very high field and uses niobium-3 tin. The other coils in there use niobium titanium. This is a really big machine. You can see the scale of the person here. So these are huge magnets. In fact, one of them you can see here that's been delivered already. Compared to the people in there, you can see how huge these are. This technology is very difficult. Niobium-3 tin's a brittle superconductor. This has to be made by a wind and react technology, and so the whole magnet had to be heat treated after it was wound. It's not a simple task at all. So where do we go after ITER? ITER is going to, it is a big experiment really. It's not going to produce power to the grid, but it's going to test lots of different things about that need to be tested about a fusion reactor. The timeline, there's the standard roadmap that we have that's been around for a long time now, is that ITER might have its first plasma about 2025 and will do its first sort of DT fusion reactions about 2035. So we're still talking just over 10 years away. Where to next? The next stage in the general roadmap is the demo magnets, demo class. ITER is one machine that's being collaborative project between lots of different countries. Demo, at the moment, designs are being put forward for demo for all different components of that international team. So there may end up being lots of different demos. These are about 1.5 times as big as ITER and use about the same magnetic fields. And we're talking on a time scale, maybe starting operation about 2050. But these still are not producing power to the grid. That might come at about 2060 in this standard roadmap. So this is still a long way in the future, and these machines are getting bigger and bigger and more difficult to engineer. So is there an alternative? Well, if we look at this fusion power, the way that demo is getting more fusion power is by increasing the radius, because fusion power scales with radius to the power 3. But as I've mentioned already, it also scales with magnetic field to the power 4. So if we could use higher magnetic fields, we might be able to increase our fusion power that way. And if we have a look at the phase diagram on the left-hand side here, irreversibility field is a function of temperature. The operating space for niobium-3 tin is down here. We can't operate at very high fields or very high temperatures. But if we went to something like IPCO or other REBCO, rare earth barium copper oxide superconductors, we could expand that operation space to much higher fields and higher temperatures, which for fusion would be very beneficial. So the idea here is that if we employ REBCO high temperature superconductors instead of niobium-3 tin, we could use higher magnetic fields, higher operating temperatures, with the hope of making smaller devices which are cheaper and can be developed on a shorter time scale. So there are some projects that are looking at using HTS for fusion already. I know of 3 that are building systems or in the design phase of doing that. One is Tokamak Energy in the UK. This is a private company. Another is Commonwealth Fusion Systems in the US. Again, another private company. And the third project that I'm aware of that's confirmed that they'll use HTS is the STEP project in the UK, which is a UK government-funded project, a spherical tokamak for energy production. That's what STEP stands for. So where are these, what's the material that these reactors will use? It's REBCO in the form of coated conductor. Now I'm not going to talk very much about that. I think there's a talk on coated conductors after this. So essentially it's a flexible metal tape using multi-layered technology in order to get the REBCO superconducting phase in the correct crystallographic alignment and with enough flexibility to wind it into magnets. So here is a schematic. The REBCO layer is a 1 micron thick layer in the middle there. There are lots of manufacturers of this product. Some of them are here. You won't be able to read the details, but they all use slightly different technology in order to achieve this kind of multi-layered tape. In the US, the Commonwealth Fusion Systems have been building have built a test coil, model coil, for Spark, which is their sort of half-scale demonstrator project. This is a 20 Tesla magnet that they've shown can get to 20 Tesla at 20 Kelvin. It used 267 kilometers of coated conductor, which is about 1/5 of the global annual production of coated conductor at the moment. So you can see that if we're going to develop more of these compact fusion machines, we're going to have to upscale the coated conductor production very considerably. In the UK, Tokamak Energy have also been very busily working on a magnet program. They've been using some technology that they've developed on non-insulated coils or partially insulated coils, which are a bit different to the standard type of coils. They're working towards this demo for their magnets called Demo 4, and they've been busily building the coils, the TF and the PF coils for this, and you can see in February they released this press release showing some of their coils that they've made in preparation for this Demo 4 reactor. Okay, so let's move on to radiation damage, which is the main topic. So REBCO, what I'm going to look at now is the defects that we form in it when we hit superconductor with neutrons or other projectiles. So in the fusion reactor, we have deuterium and tritium reacting together in the plasma to form helium nuclei and a neutron. And these neutrons are very high energy, about 14 megaelectron volts. Because neutrons are neutral, they don't interact very strongly with materials, which means that they pass through. They can pass through the first wall, some of the shielding, structural materials, and they'll get to the superconducting windings, particularly in a compact reactor where there's not very much space for all these components in front of the magnet. So we are going to have fast neutrons going through our superconducting windings, and we need to know what that's going to do to the superconducting properties of the magnet. So there's been quite a long history of looking at neutron irradiation studies on high-temperature superconductors, which went back to the 1990s. A lot of work was done in Vienna using their Triger reactor, which is a fission reactor, to generate the neutrons. So initial work was done mainly on single crystals and polycrystalline bulks, but since about, I think, 2008, Michael, I think is in the audience, he can correct me if I'm wrong, they started looking at cotoconductors in the Triger reactor. And they've looked at various different manufacturers of cotoconductor, which all have different microstructures. And there's a series of publications that have come out of the Vienna group. There's also been some campaigns in the Prague reactor. I'm not going to talk about those today. Today I'm going to talk about some of the results that have come out of those Vienna irradiations. Just so that you can see, a fission reactor doesn't produce the same spectrum of neutrons as a fusion reactor would. And in particular, we're interested in these fast neutrons, which are about 36% of the flux. So here's a graph from the Vienna group that shows how cotoconductor properties change with fluence of neutrons. So this is how many neutrons have gone through the material, essentially, per unit area. So the transition temperature, this is normalized, so the transition temperature decreases monotonically with the amount of neutron damage it's seen with the fluence. But the JC, or the IC of the material, does something a little bit more interesting. So this is in high fields at 15 Tesla. The critical current density goes up before it comes down again, which is quite interesting. But we'll have a look at why that might be the case. So I just want to take a step back and look at what happens when you have something irradiating a material. This is just a standard picture that's used for metals. Most studies on radiation damage have been done in metals. So what happens is we can create lots of defects. We've got neutron or other projectile coming in. The kind of defects it can produce are vacancies like this. It can produce interstitials like this. But it also produces these cascade defects, where one ion is knocked out and it knocks out another atom and knocks out another one, and you get this big cascade, and you end up with these sort of damaged regions like this. If we look at a molecular dynamics simulation done by Sam Murphy in Lancaster, you'll see what happens when a projectile hits something like IBCO. So what you'll see is one projectile coming in, knocking one atom in the structure, and then every coloured dot you see will be an atom that's been pushed out of place. So you get something like this happening. This is this damage cascade I was talking about, where each of these dots is something that's in a position where it didn't start and isn't on a lattice site anymore. So you end up with these regions like this, which are these cores of the damage cascades. We can see them in the TEM. So this is a microscopy done by one of my DPhil students. Here are the kind of features that are those amorphous regions that are caused by these damaged cascades. You can see them in other imaging modes as well in the STEM. It depends which imaging mode we're looking at. Here's one of them here in a bright field image. The interesting thing, though, is that this doesn't really explain what's going on with decrease in critical temperature. So these big features here, these can explain what happens with the critical current density, because these things are excellent flux pinning sites. So as we put more of these in, actually our critical current density goes up because we get stronger flux pinning until they get too close together, and then critical current density comes down. But TC is a property of the matrix. It's a property of the majority of the material, which is where the current goes through. So something must be happening in these regions that still look relatively perfect. And that's one of the questions that I've been looking at. What kind of damage is going on in those regions that we can't see in the TEM? So here's just a schematic to explain what's happening in these when we do this irradiation. You'll see that before irradiation we might have some strong pinning defects already there in the material. We've probably got lots of point defects that do these weak collective pinning. When we irradiate it, we produce these damage cascades, these things here. They'll produce additional flux pinning centres at low fluence, but at higher fluence you might end up with increased flux creep, which will decrease JC. The point defects also increase in the matrix. We get more point defects in here, which reduces TC and will eventually reduce JC at high fluence as well. So what's the effect of the microstructure of the coated conductors? Well, if you look back at this plot, there's different kinds of coated conductors in here, and the two lines in red and orange have artificial pinning centres, which are things like barium zirconate nanorods that have been deliberately added into the structure. You'll see that the enhancement you get in IC is not as good when you've got these advanced pinning centres already in the tape. The Vienna group have explained this by looking at the amount of damage you've got on this axis compared to JC. When you start the material, you've got some sort of damage already, some sort of defects already in there, and so JC is somewhere here on the curve, and when we irradiate, we push it up a little bit further before it gets worse again by adding these extra defects. However, if we were starting with artificially pinned superconductor, we're already further up this curve when we start. We put extra pinning centres in to start with, so we can't get much more enhancement when we do the irradiation. That's the explanation of why artificial pinning centres don't seem to, you don't seem to get so much JC enhancement. So what are the challenges with these neutron irradiation experiments? So you'll see that a lot of the experiments I showed you came out of sort of one set of irradiations done in Vienna. There's not very many neutron irradiated samples available, coated conductor samples available to look at. The samples are radioactive once they've been neutron irradiated. The campaigns are expensive, they take a long time. When you've irradiated your samples, you then got to wait before you can do lots of the testing on them because they're too radioactive. It's quite difficult to do things like in situ measurements in those kinds of reactors. And of course, a minor point really, but an important one too, is that the energy spectrum for fission reaction neutrons isn't the same as the fusion reaction neutrons anyway. So the fusion spectrum has a peak here at 14 MeV, whereas the fission spectrum is fairly flat and has maybe a little bit more of these fast neutrons, but not very many of these high energies of 14 MeV. So what could we do instead to mean that we can get more results more quickly and more easily? We could use ion irradiation instead. So they're much more widely available, ion sources. You've got a wide choice of what ion you use and what energies you use. The samples don't get activated unless you're using protons. And you can get much higher damage rates much more quickly because they're charged species, so they interact slightly differently with the material. It also makes things like in situ experiments much easier. Disadvantages, of course, are that they interact differently with materials. You've got both electronic and nuclear interactions, whereas with neutrons you just have these nuclear interactions. They've got shorter penetration depths, which means we have to design our experiments a little bit more differently. And we would expect that the defects that they produce might be different to those that you get with neutrons. And that's the question that we've been trying to answer, is how different those defects are. So a standard picture would say if we use light ions like protons or helium ions, you might get small diffuse cascades. Heavy ions may make these bigger cascades that are a bit more like neutrons, but there are other issues with using heavy ions. So how good are light ions, for example, as a proxy for neutrons? Well, if we plot what happens to TC, or the change in TC on irradiation, as a function of fluence for different species, we find that it looks very different on this graph. So neutrons have this gradient here, and our helium ions that we've done in Oxford, a much steeper damage rate, and protons also quite steep. So what's going on here? Well, because these different projectiles interact differently with our material, they produce damage at different rates, and we can use simulations, Monte Carlo simulations, for example, to work out how much damage we would expect from different ions of different energies. And when we do that calculation, we can convert our graph on the left here to something in terms of average damage, which we measure in something called displacements per atom, or DPA, which is how many, on average, displacements of atoms within your material you have as a result of that irradiation. So if we do that scaling to a DPA scale now on the x-axis, now our ions look to be having much more similar effect to the neutrons in terms of the change in TC. So that's encouraging in terms of using ions as a proxy for neutrons, that at least we've got some scale that we can compare the damage on. So how are we going to look at these radiation defects? If we want to see if they're doing the same thing, neutrons and ions, we need to look at what kind of damage we're creating. And in Oxford we've done that with electron microscopy, but also some X-ray absorption spectroscopy, which is what I'm mainly going to talk about today. So here's some electron microscopy. The left is a sample that's is unirradiated, a coated conductor that's unirradiated. Here is the irradiated version. This has been irradiated so much with helium ions that it now no longer superconducts. However, I think you probably noticed that every sort of atom column you see in the pristine structure is also there in the irradiated structure, so it's not completely damaged the material. You can look here if you want to see which atom is which. You see all of the cations in this kind of imaging mode. We don't see the oxygen ions because they're too light. So we can be pretty sure that the cation lattice isn't really completely damaged by this irradiation, even though superconductivity is all gone. So we started thinking that maybe, and a lot of the literature has mentioned this already, that the oxygens can move around much more easily than the cations. And so probably the damage that's causing the TC degradation is because of oxygen defects. And we can't see that, certainly in this imaging mode of the TEM, and it's pretty difficult to see it in any imaging mode, actually, those oxygens, when you've got such heavy cations in close proximity. So instead of doing electron microscopy, we've looked at other techniques where we can get some handle on what's going on with the oxygens in the structure. And the method that I've been using is using high energy resolution X-ray absorption spectroscopy. So absorption spectroscopy is sensitive to local chemical and structural changes around a particular chosen ion in your structure, or atom in your structure. And here we've been looking at the copper environment. So we've been using hard X-rays to probe the chemical environment around the copper atoms. And we do it with an experiment at diamond light source that looks like this. We scan the incident beam energy across the absorption edge, and we detect what's going on using fluorescence. So the process is this: we take our an electron in the copper 1s state, gets excited by the incoming X-ray into the 4p unoccupied levels. You leave a core hole in the 1s state, and so a 2p electron falls down into it and will emit a K-alpha X-ray. So we detect the K-alpha X-ray that's coming in, and the intensities of those tell us about the absorption process that went before. The kind of information we get looks like this. So this is complicated, but I'm going to explain what I want you to be able to see. So the black line in here is the experimental data. This is when we put our X-rays in a particular angle to the coated conductor surface. so that we've got our polarization of those X-rays pretty much along the C-axis of the unit cell of the superconductor. So we're going to be probing bonds that are positioned along that C-axis direction with this graph. With this one, we're probing. We put our electrons in. We put our X-ray into different angles, so our polarization is roughly along the A-axis. So we're probing the bonds along the A-axis. What you can see is that we get all these features, lots of different features along this edge. It's not just one feature where we get the absorption. So understanding what's causing those is quite tricky, and to do it we need modelling. And we've used density functional theory to model this absorption process using core hole calculations. And what you can see first of all is that we can split our model into components that are coming from the copper in the planes of the structure, which are these planes in the Rebco structure, compared to copper that are in the chains along here. So we can see straight away that these features along the rising edge along here are coming from the copper 2 atoms in the structure, the copper planes. If we look at this one, a lot of these features are coming from the chains, but this peak has a large contribution from the coppers in the plane again. So what happens when we do the irradiation? Well, there's various graphs on here, but essentially the pristine sample and argon irradiated and other things are shown here. They're all very similar, apart from the green one, which is a heavily ion irradiated sample. So it's the sample that I showed you the electron microscopy from earlier, where it looked like all the cations were still where they should be. So if we look at the differences we're seeing them in these peaks along the rising edge. And that suggests that these are effects that are happening to the copper 2. So things are happening around the copper planes, within the copper planes, that are on irradiation, so defects around there. This peak also decreases a lot, and that's mainly due to copper 2 as well. So our first conclusion really is that this irradiation is causing defects in the copper 2 planes. It might be causing defects in copper 1 as well, but we've definitely seen them in copper 2. To compare with, we've looked at some samples that have been argon annealed instead of irradiated, because with argon annealing, we know we pull out oxygen, but we know where from the structure that oxygen comes out. It comes out from what we call the O1 sites. And so we're using that as a little bit of a comparison for our model. If we want to find out a little bit more about the defects that we've put in, we can do some rather clever things with the DFT modelling. We can create supercells and make defects in those supercells, and then we can simulate what the spectrum would look like for particular defects that we put in. So we've done various different kinds of defect, and we homed in on a couple to look at, in particular this Frenkel defect here and the interstitial, because when we do X-ray diffraction, we see that the C-axis gets expanded experimentally when we do these irradiations. So we particularly wanted to look at defects that cause that expansion in the C-axis when we do the modelling, which is what we see from defects that have this interstitial oxygen in this site here. So we're particularly interested in those ones. And when we do the simulation, we can see what differences we'll get. So again, this is complicated. The black lines are the experimental data. The black line here is the modelled pristine structure. The red line is the Frenkel defect model, so what we would see if we had the Frenkel defects there. And the blue line there is the O1 vacancy, so that's pulling out the oxygen from this site, and that's what happens when we argon anneal. So we're using that as a comparison. Now, I don't expect you to be able to work out whether you think that we've got some Frenkel defects in there or not based on the changes with the spectra, because it's much more easy to see when we do the different spectra. So now, if I plot this a little bit differently, here, on the top I've got the experimental data. This is the irradiated compared to the pristine, the different spectrum, and I've got the Frenkel model different spectrum here as well. So you can compare the model with the experimental data. And certainly in this orientation, the kind of shape of the changes are quite compatible with the Frenkel defect. This one and the other orientation is less clear, so maybe something else is going on as well. If we look at the argon annealed data, again, this is the black line is the experimental data for the comparison between argon annealed and pristine samples, and the blue is the O1 vacancy model. And again, we see roughly the same peaks and troughs in the same place in the model and the experiment. And in particular, we get a very nice match in this direction. This peak here, incidentally, is caused by copper in the 1+ oxidation state, which you get when you pull out that oxygen. And we definitely don't have it in our irradiated samples. So we're not just pulling oxygen out like we do with the argon annealing. So we've got some idea of what kind of defects might be in this sample. I wouldn't say we've found exactly what's going on, but we've got some ideas about what kind of defects there might be. So what happens with neutron irradiated samples in comparison? Well, on the top here are on the bottom is our iron irradiated, just like I showed before, the different spectra. And we've looked at some of the samples that Vienna irradiated. Two samples, one is a Sunam sample and one's a superpower sample. And you'll see that actually, if you look at the shape of the different spectra, it's really very similar. It's very striking in this orientation, that the changes are very similar with neutron irradiation compared to helium irradiation. So it wouldn't be crazy to think that we might be producing the same kinds of point defects in the neutron irradiation compared to the helium ion irradiation based on this very similar spectral changes that we see. Okay, so I'll move on to the final part of the talk, and this is some in situ cryogenic irradiation. So of course, most of this irradiation you've seen so far, in fact all of it you've seen so far, has been done at room temperature or slightly above. And in operation in our fusion magnet, the superconductor is going to be at 20 Kelvin or that kind of temperature. And we were interested in how that affected the defect creation in these materials and the superconducting properties. And we've looked at this not by irradiating cold and then warming up, because there's a chance that your defects might move around if you do that. We've actually done in situ experiments. So here we've gone to the Surrey Ion Beam Centre. We've taken samples that we've packed into a track like this so that we can do JC and TC measurements on them. We have ions coming in from the accelerator, and we can irradiate and measure cold without warming up in between. So this is work that was done by Will Iliff, who's now at UKAEA, but was a DPhil student with me in Oxford. We've used helium irradiation again for this, slightly different energy than the spectroscopy I showed you, but still helium ion irradiation. So what did we see? Well, this is JC normalized as a function of damage in this dPA scale, so converted to displacements per atom. And what you see with all these different samples that we've cold irradiated is we get this rather similar rate of degradation of JC as a function of damage. We don't see the peak that we saw in the other data because this is measured at self-field, so you wouldn't expect to see that. But how does that compare with warm irradiated samples to the same damage level? So we've done that, and if you look at the red points, these are all ex situ room temperature irradiated samples. You see we get a pretty similar damage rate actually, apart from this anomalous sample here. But there's something very interesting that goes on with the cold irradiated samples. Because if we irradiate down to here, and then we warm up to room temperature, and cool down and measure again, we see it's got better. So it's actually improved its JC by this excursion to room temperature. And that's a defect annealing effect. We can irradiate it a bit more, and anneal it again, and get recovery again, partial recovery. So in fact, even though it looks like the damage rate is similar in these two warm and cold irradiated samples, I actually don't think the damage landscape can be the same, because we can't recover the properties of the room temperature irradiated samples, but we can get some recovery with the cold irradiated samples when we go to room temperature. TC does a similar thing. I won't spend very long on it, but you can compare what happens to TC degradation in the room temperature and the cold irradiations. And we also get this recovery in TC here when we go to room temperature if we've cold irradiated them. So what do we think is happening? Well, if we look at the critical current density, it does this. We go to room temperature and it gets a bit better, we irradiate again. What we think is happening is that we've got different kinds of defects being put in there during the irradiation. Some of them have low activation energies for migration and annealing, and others have much higher activation energies. So when we go to room temperature here, we can reduce our defect population, but it's only the low activation energy defects that can recombine and anneal out. So we reduce it, but we don't go back to zero, because we have other defects that can't be annealed out at room temperature. If we go to the end here and we do a higher temperature anneal, 420K anneal, we can recover a few more of the defects. It gets better again. Okay. So some of those low activation energy defects, we don't know what they are, but I can speculate that one defect that we might put in is this one. These are the copper chains in the structure. You could easily get an oxygen moving here to that sort of vacant site there. And I think that would be a very low migration energy process to get that to move back and form the chains again. So for that to move back there, I think we wouldn't need very high activation energies. So that kind of defect might be recovering quite easily. So there's been other studies on annealing. These are recent studies by the Vienna group on two different samples here, one Tsunama, one superpower. What you're looking at here is TC as a function of annealing temperature. So you can see if you've got unirradiated samples, you're not doing any damage by doing this annealing. It's being done in oxygen, so we're not pulling oxygen out. However, if you've got the degraded irradiated sample and then we anneal, we can see we're getting TC going back up. That's very similar to the kind of recovery that we were seeing in the cold irradiated samples. Out of interest, this is the argon annealed sample, so you can see if you anneal an argon, you pull out oxygen and it gets worse. Same thing happened with the superpower samples, but something odd happened with this sample here, so I'm not entirely sure they couldn't carry on getting this in recovery here. What happens to JC? Well, this is a rather complicated diagram, and I'm not sure that I've got the explanation right, but I think what's going on is that we get this initial increase in JC when we do the annealing, because we're annealing out point defects, which is increasing TC, and will increase JC as a result. When we get a bit higher in temperature, we might be annealing out some of these larger pinning centres, so some of these defects that we put in that are larger. And if we do that, then we're reducing flux pinning and JC will go down again. There's another peak here. I'm wondering if this is to do with defects that have higher activation energies, for example, which can then be affected at higher annealing temperatures. Okay, so the final thing I want to tell you about is some recent experiments we've done with the beam on. So the experiments I showed before were we irradiated them cold, and then we turned the beam off and we measured JC with the beam off. We do these with pulse measurements, but we can also try to do the measurements with the beam actually on. And the measurement's slightly different. What we did was with the beam on, we started ramping up our current pulses in magnitude until we started seeing a voltage, some instability in the voltage. And then we backed off a little bit and did a whole series of pulses at the same magnitude of current. And during this, of course, the sample's being irradiated, so we'd expect it to be getting worse, be getting damaged, and so what we'd kind of expected is that we would see no voltage here, and then we'd start seeing a voltage as the damage comes in. What we actually saw is something like this. Now, this is a complicated diagram. It's damage as a function of various things here, but what I see mainly. So here is the series of experiments we did with the beam off. So we turned the beam off and measured. And after the first time we did that, we started measuring during with the beam on. And here's our increasing current. We see a voltage when we back off. So that's that measurement I told you we were going to do. But what you might notice is that we're nowhere near the current that we could get with the beam on, with the beam off. When the beam's on, we're about a third of the current that we can get with the beam off before we start seeing this voltage. We're trying to work out what the reason is for this. We've got some speculative reasons. We don't think it's just the whole sample's heating up because of the energy of the ions being deposited. We think it is an effect of some sort of interaction with the electrons in the system, energizing those and then breaking Cooper pairs essentially to reduce superconductivity locally. But we're only speculating at the moment, so we need to do more of these experiments. The MIT group have also done some experiments that are not published on this, and they see a little bit of a degradation, but nothing quite like we see. So there's work ongoing to try to explain this. So to summarise, compact fusion, which we're hoping will help accelerate the timeline for getting fusion reactors require high temperature superconductors because they have to operate in this higher temperature, higher field regime. We urgently need to know how long those superconductors are going to last when we put them in that environment. And we have some data, but we need more. And what we've been doing in Oxford is really trying to understand what defects we put into those materials when we do the irradiation, partly to find out whether we can use ions as a proxy for neutrons and where we can and where we can't use ions as a proxy for neutrons, to try to look at these in situ conditions which are closer to a fusion reactor in terms of the temperatures that are operating at, even if we're not using neutrons. So with that, I shall finish and show my acknowledgements, and happy to take any questions.
Thank you. Are there any questions?
Yeah, I just wondered for the last result you mentioned, the degradation, there's a significant, so that's with neutrons, right?
That was with ions, with the ion. So the interactions are very different than it would be with neutrons. Yeah.
So because I was going to point out that there's a spin, neutron spin, which interacts with the electron spin and will degrade superconductivity by breaking two pairs via the stage.
Okay.
But I know for ions, I guess I don't know.
So my feeling with ions is that because they interact electronically, they can transfer energy to exciting electrons in the system, and then they thermalize and break Cooper pairs as they go. That's kind of what the detector people think happens. I mean, when they use their photon detectors, whether or not that's exactly what's happening here, I'm not sure. And of course, with neutrons, that particular interaction wouldn't happen. But as you say, there may be others. And certainly where we get those damage cascades with neutrons, we would expect superconductivity to be disrupted locally for some time period, which, again, I don't know if anybody does the right kind of modelling for this, but we don't do that in Oxford. So working out what kind of volumes of material and over what sort of timescales might be affected would be an interesting thing to do as a result of those neutron collisions. But I haven't thought about the spin yet.
Some years ago we published a paper in which we showed that a destruction of superconductivity by zinc impurities operates by breaking the degeneracy of the in-plane oxygens. And this is exactly the same mechanism by which the LTO and the T-tilt destroys superconductivity. So I would bet that your C-axis oxygen is actually a proxy for the breaking of the in-plane oxygen degeneracies.
You mean in the spectroscopy?
Yes, what you said, yeah. I think that is the mechanism, that your irradiation breaks the in-plane oxygen degeneracies, and that is why the TC drops.
Yes, I think I agree with you that we're definitely getting this change in the in-plane oxygen. I think our results are quite clear. Which, interestingly, the earlier literature assumed that it might be the chain defect oxygens that were being affected rather than the ones in the plane, because they're the easier ones to move. But here I think we've got some clear evidence that the in-plane oxygens are moving around. Yeah.
One more here.
Here.
Susie, you mentioned in the introductory part that the neutron spectra produced in the fusion reactor and fission reactors are different. So is it known which of these two is more damaging to superconductors?
I don't think experiments with 14 MeV neutrons haven't been done because we don't have a source of fusion neutrons, certainly a high enough flux source of fusion neutrons. Certainly, Michael can tell you more, but certainly the fission spectrum neutrons, they've got to be very careful with the thermal neutrons that are there that are produced as well, because particularly with gadolinium, there are particular reactions that happen that are much more damaging with those thermal neutrons. So they shield those out if they want to look at the effects of the fast neutrons using fission spectrum. But there is no high enough flux source of fusion neutrons to do the experiments in, so nobody's done them.
But what's your guess?
I wouldn't like to guess.
Thank you.
There's one more.
Okay. We use some in situ resistivity measurement in iron-based superconductors of beam. But when we measure beam on, we have a lot of noise. In your case, you could measure JC. Do you use a special kind of electronics to measure this?
No, so I wouldn't say we're measuring JC actually in those beam on measurements. What we're doing is we're sitting at one current and we're pulsing it, and we're looking for when we pick up some sort of voltage signal. So that isn't the same as saying we've measured IC. So I didn't say that we find that ICs drop by a factor of 3, but we're certainly getting instabilities in measuring at those kinds of, at much lower currents. So it might be a similar effect that you're seeing when you're getting the noise. Yeah.
Thank you for your talk. Could you please comment on the time required for annealing? Or the time required for annealing of your samples, comparing to the damaging time?
Okay, so with our experiment, when we've done the annealing at room temperature, that can be, so what we normally do is we irradiate at the beamline. That can take a few hours to get to the flux we need with ions. We then take our sample back to the lab, and the next day we cool it down again. So it's a one-day annealing at room temperature does this. We've done it for longer, and of course you get slight improvements for longer times, but most of the recovery happens in the first day.
Can you accelerate by heating?
You can heat it, but you've got to be careful not to pull the oxygen out. So yes, you can accelerate it by heating a bit further. Yeah. All right.
Very interesting. Very simple question. Why the electric power coming out from this tokamak?
Why is there
proportional to P4 to the horsepower?
Oh, I don't know the answer to that. Sorry, I'm not a fusion expert, a plasma physicist.
Okay. And to your last slide, what is your guess? How long those equipment can last with these magnets at today's technology?
Well, that depends how much shielding are put into the designs. So I think that's exactly the question. That they'll have a lifetime they need their magnets to survive for. How much shielding do they need to put in to make the materials last? I don't think we're at the point of knowing quite yet what that will be. So. Thank you. Oh.
Quick question. Have you also done energy loss spectroscopy for the oxygen in some of these materials?
Yeah, so in the TEM you can do energy loss spectroscopy, which is exactly the same actually as the absorption spectroscopy in terms of the physics. We've done a little bit, but in our microscope, so the nice thing about that is that you can get spatial resolved information. And we've tried a little bit, and I know that other people have been successful. In our microscope, when we did it, we couldn't get enough signal. So this is on our to-do list for the next couple of years to work on that. Yeah. Thanks.
When you're considering the annealing and recovery of TC, of course, an optimized TC requires an optimization of the oxygen stoichiometry.
Yes.
And so that requires usually oxygen at high temperatures. So how do you take this into account compared to your experiments to recover TC?
So when we do the annealing, if we're going above room temperature, if you just did it in air or you did it in another environment, you would put out the oxygens, and yes, you would decrease TC. So those annealing experiments are done in oxygen to stop that happening. The room temperature anneal, we don't do that because at room temperature you don't really put out oxygen. The oxygen's not very mobile there. So it doesn't get pulled out at a very fast rate at room temperature. Yeah.
So you're not doing neutron bombardment. How do you use a megawatt laser, which is much easier for the experiments? You have gamma rays, that's what's coming out.
Because gamma rays, yes, but they'll interact differently to neutrons, so it's a question of what's the best proxy. Are ions a better proxy? X-rays are very different to ions. No, but ions are known from, there's been a lot of radiation damage experiments on other materials which use ions as proxies, because, yeah.
Let's thank to the speaker.
Thank you.
inviting plenary speaker Masahiro Yamashita, Tohoku University, Japan,